had a logic question, if you
Sure.
don't mind.
Yeah, yeah.
Let me see if I can paste it in the chat. This is like from my logic textbook, my formal logic class, and it was an exercise that we had to prove this logical theorem. I just pasted into the VC chat. It's like
Okay.
there exists. So yeah, I mean I don't know. I was kind of struggling proving it.
Let's see. Um,
Yeah.
there exists. I'm probably not going to be a whole lot of help here without like looking up a bunch of stuff. Is that like the implies symbol?
Yeah,
Yeah.
yeah. We use a slightly different notation
Yeah, that's
in
fine.
my class.
When I took logic, my professor wanted to thoroughly drive that the symbols have no meaning, and so my professor they uh, changed all the symbols into like stars and triangles and stuff, and it was a notational nightmare. Anyway, so what is your dot symbol? Is that like or
That's a and.
and and okay? So
Yeah.
just do an and symbol, not g of x. Gotcha. Okay. And so this is what a I guess a tautology. Is that what you're trying to get at?
Yeah, I mean, it's like, okay, well, if there is x, such that if fx then gx, then, it's not the case that for all x, fx and not gx, because, fx and not gx and
Mm-hmm.
fx and gx, those are inconsistent. Because, if we have the conditional, then we know we can't have the true antecedent and false consequent.
Mm-hmm.
So, I mean, like, it makes sense, like, but, like, I don't know, I was just struggling to prove it. But he
Yeah.
gave us, like, I mean, oh, wait, sorry, but he allowed us just, like, we have, like, five rules of inference, like, modus ponens, modus tollens, and then he gave us, like, the universal quantifiers, so he gave us,
Mm-hmm.
like, and there was, like, universal instantiation, existential instantiation,
Mm-hmm.
and,
Mm-hmm.
actually, I kind of forgot the rest, I don't know. But, and then there was also, like, some rules of inference that, like, you derive from the truth conditions of like the disjunction and the conjunction. So like for example, if we have like uh P, like I don't know, P and Q, then we can infer it, not if P then not Q.
Well, so
So like
yeah.
something like that.
So the proof of this is going to be determined on what axioms you're starting with or what theorems you already know, right? And so
Right.
I wouldn't know what how you're going to do this proof without knowing those exact axioms or those theorems. But I believe I see the trick that should probably be used, assuming that you're allowed that you're given these things, right? So, like in particular, you should probably throw a negative in, right? Um, so right here, you can make this not for all not, right? And then you can have a not there, and then you have your g of x. And so not for all not is a there exists, right? Um, and then this is distributes. So you get not f of x or g of x.
Well, I'm sorry, can you like move the paper a bit, like center it?
Oh, geez, my
Cause
bad.
like yes,
Yeah, my bad.
very good. Okay, there we go.
So I just threw in a not and a not, right? And then not for all not is a there exists. And then this not distributes, and you
Yeah.
get not f of x or g of x, right? And then I'm pretty sure this is equivalent, right? Isn't f implies g the same as not f or g?
Uh, if
Yeah.
not F then G. Yeah,
Yeah. So this
yeah, yeah.
turns into there exists f of x implies g of x implies there exists f of x implies g of x. And that makes this a tautology because this is of the form p implies p.
Mm.
And so you're done, right?
Oh, well, I mean, well, usually what he would do is like Like either if we had to just like prove a conditional, like he would start off by just like assuming the antecedent of the conditional, and then like
Mm.
proving the consequent from that, and then he would just like conditionalize. So then he
Oh,
says, oh,
okay.
if our original antecedent, then our consequent, either that or he would do proof by contradiction. So I mean, I was wondering, is there any way, like, do you know if you can like know how to do it with one of those methods, or like maybe you do like a proof by contradiction,
Well,
or
sure, you can. Yeah, sure, you can do that, right? Um, yeah, like I'm saying, there's a bunch of different ways to prove this, and it
yeah.
depends on the starting axioms that you begin with. So if you're allowed to do proof by contradiction, then that's the way that you would do that, right? Um, the main thing here is that this is a general form, right? So I assume by proof your professor means to demonstrate that it's a tautology. So whatever way you're proving this, you're going to end up with a tautology at the end, a zeroth order tautology typically. Um, and so uh, the point is that this is a theorem in all possible first order logic systems, regardless of the interpretation of x, f, and g, and that's why that's very special, because as I assume, I don't know if you've gotten this far in your class or not. Not every statement is a tautology in first order logic, and some of the statements may be true in one system and then not true in another system based on whatever the interpretation of f, g, and x are, right?
Hmm.
Yeah. So the point is
Well, I
that,
mean,
yeah,
like,
all I'm saying is that if you give me something very general, that means it better be able to be proven basically in first order logic sorry, zeroth order logic principles, or else you wouldn't be able to prove it, right? Not without knowing what F and G stand for, right?
mm. Yeah, I mean, my professor, like, when he said like to prove like that like a particular statement was a theorem,
Mm-hmm.
like what he meant by that was like I mean, the way he said it, like, the theorem had to be proven by gamma, where gamma is like the empty set of premises. So like we'll start off by like making like one or two assumptions,
Mm-hmm.
right? Or yeah, we'll start off by like making a certain number of assumptions, and then as we like progress through the proof, we want to conditionalize those assumptions. So like we want to put those premises in the antecedent of a conditional, so that way we discharge our reliance on that assumption. And so
Uh-huh.
that's usually what he means, like and that's what he meant when he said to like prove it as a theorem. So I mean, like, I mean, I can show like an example, like,
Right. Well, yeah, I'm just saying that if you're given a general statement like this,
yeah, yeah.
the only way that this can be proven is if it resulted in a tautology, right? So
Mm.
let me just give it to you this way. How would you prove there exists an x such that f of x implies g of x? Like, how do you prove that that's
There
true?
exists. I mean, I guess you could try. Let me there exists x such that f of x. Maybe try like proving by contradiction. I mean, but then like, actually, I don't know. How would you do that?
You can't. You can't.
Mm.
What is missing in order to prove this? You don't know what f and g mean. So, for example, let's imagine we're talking about numbers. There exists a
Mm.
number such that um, if n plus 1 is less than 5, then n is less than 4. Okay? Is this a theorem?
Yeah.
Is that true of natural numbers?
Yeah.
It is. So this can be proven, and it's exactly this form. It's this statement, and it's true. It's true. But what if I did there exists an n such that if n squared is less than, negative 2, I'm sorry, 3, then n is greater than 10, right? So is there an n such that if n squared is less than 3, then n is greater than 10?
No.
No, there's no such n. So this is false. And yet these are both the same form, right? They're both the same form, right? It's a different f and g for each of these statements, right? It's like, F1 for this one and F2 for that one and G1 for this one and G2 for that one, right? But the point is that it's the exact same formula. So this is called a well-formed formula, right? Well-formed formula, a WIFI, right? But this is called an interpretation of a well-formed formula. Now, in zeroth order logic, when you do, i.e., propositional logic, there was no distinction because in zeroth order logic there were no variables. You had p's and q's and r's, ands, ors, and that's it. There wasn't any variables. So there were no objects to speak about. There were no objects that had properties, right? And so in zeroth order logic, there was no distinction between interpretation and the well-formed formula. And so it turns out in propositional logic that a statement is a tautology if and only if it can be proven from the axioms of propositional logic. And that's just a fundamental fact. There's no interpretation needed. You don't need to know what the P's and Q's and R's are, right? You can prove everything you want to know about propositional logic because it is all the tautologies, right? So what you're experiencing here is first order logic. This is first order logic. And the fact that first order logic, if it can be manipulated into a first order logic, a zeroth order logic statement, then if that zeroth order logic statement is a tautology, we call that statement in first order logic also a tautology. There are plenty of statements in first order logic that have nothing to do with a tautology. They're not reducible to zeroth order logic at all, like this one, and they don't have a truth table to speak of. That doesn't even make any sense, right? There's no truth table I can do here, right? And hence, we now have to introduce a much more complicated concept, which is that when I have a well-formed formula, that well-formed formula has to be interpreted in order to figure out if it's true or false. So well-formed formulas themselves are not just naturally true or false unless they fit exactly what a zeroth order logic statement would look like, right? But any one that doesn't do that, it can be interpreted, and the interpretation determines if it's true or false. Does that make sense?
Yeah.
Yeah.
Okay. Yeah. So thank you for that clarification.
Yeah, yeah.